See, this is Kiliani Fisher synthesis. So, in this lecture, I will try to I will explain some chemistry through which we can do certain reactions on carbohydrates. And remember one thing: these are the biologically active molecules. So these are not so simple reaction as we have gone through in the synthetic organic chemistry. Here very specific reagents are required, and if a little bit difference in the selectivity of the reagent, then you might not get the desired product, right? So in this case, no general reaction, very specific reactions are known. So this Kiliani-Fisher synthesis, this is used to increase the number of carbon atom, one carbon atom, right? So this reaction, this is used to increase the number of carbon atoms, number of carbon atoms in the molecule, or in the carbohydrate molecule. Right? So for if you have pentose sugar, so pentose, so you can convert by this reaction into hexose, right? So see what chemical reactions are involved here. See, if you take this, uh, suppose that some compound, cyano compound, suppose that or compound like this, if you have cyano compound, then if you take H2, palladium, barium sulfate. Now all of you are getting what reagent is this? Lindlar's catalyst. So this is very selective. So this will convert into, this compound is convert into C double bond N, H, and H and R, right? And on hydrolysis, which type of compound is this? This is an imine. Imine. And on hydrolysis, this will convert into what? Aldehyde. So this group, this you have added right. So first you have to add Cl, and in carbohydrates, aldehydes and ketonic groups are there. So it is very easy to add Cl over aldehyde or ketonic group. So this is the basic chemical reaction. Now see, suppose that if we have D-arabinose. Suppose that if we have D-arabinose, arabinose is a pentose, aldo sugar, C double bond OH is there, CH2OH. So this is D-arabinose. This is a pentose sugar. 1, 2, 3, 4, 5. Right? So D-arabinose, this first you have to react this with HCN. When you react this compound with HCN, the reaction will take place at this carbon, and what, in this case you will get cyanohydrin. So this is CNH, or there are two products possible. See, this is sp2 hybridized, so there is two possibilities that Cn comes this side and the rest part is same, so I am not showing that part, and I can represent like this. So this portion as it is, and it is allowed, you can show in this way the reaction, plus CH CnH, right? This portion is, it is remains same here also. So since this is sp2 hybridized planar structure, so Cn has two orientation, one possibility that from this side and other is from this side, right? So this is the cyanohydrin. Now when you treat this with hydrogen palladium H2 palladium barium sulfate poisoned with quinone first, and hydrolysis. Both the step I am showing here. So this Cn is converted into CHO, right? Cn is converted into what? CHO, right? So how to convert this? Wait. I have made some mistake. OH and OH. Now this Cn will convert into what? Uh, so it is better to write Cn here. Don't write here Cn. Write here so you can justify very easily. Cn and H. So this is cyanohydrin, right? Now this Cn will convert into CHO. See this reaction, H2 palladium barium sulfate and H2O. So this will convert into CHO. This will convert into CHO. So you will get, see, everybody should note down, right? Now you get COH CH2OH. This part is same. This part is also same. This part is also same. And one OH this side. Now tell me, what is the name of this molecule? One, two, three, four, five, six. This is D series member, and this OH is this side, so this is D mannose, right? So from D arabinose, this is a pentose sugar, and this is a hexose sugar. And here you will get COH, COH. This part is same. This part is also same. This part is same, and this time OH on this side. So this is a glucose, so D glucose. And this is also hexose. And these two are epimers, right? These two are epimers of each other. So see how from 5 carbon carbohydrate you have prepared 6 carbon. 1, 2, 3, 4, 5, right? And here you have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, right? So in this way you can convert 5-membered sugar to 6-membered sugar, and this is known as Kiliani Fisher synthesis, right? Now see shortening of chain, how to decrease the how to decrease the number of carbon atoms. So this is what known as rough degradation. There are two methods. One is rough degradation. Rough degradation, right? See, what is this basic concept of this reaction? The basic concept of this reaction, you can convert hexose, means 6 carbon, to pentose, or tetrose to triose, pentose to tetrose, pentose to tetrose, tetrose to triose. So you can decrease the number of carbon atoms in the chain of the carbohydrate, right? Now see, suppose that if we have this type of functional group, this type of sugar, suppose that D-glucose. Suppose that we have this D-glucose, right? 6 carbon hexose. First, in this rough degradation, first you treat this compound with bromine, water. So bromine water is which type of reagent? Oxidizing agent or reducing agent? Tell. This is which type of reagent? So this is basically oxidizing agent and mild oxidizing agent. So this will oxidize this aldehyde group into carboxylic. And rest part is same, right? After that, react with this compound with calcium hydroxide. So this is a base and this is acid. So there is simply the salt formation will take place. COO Ca 1 by 2 like this. And now very specific reagent, ferric sulfate and H2O2. If you use ferric sulfate, Fe2SO4 whole thrice and H2O2, so this salt, this will convert into CHO, right? So this whole group, this will decarboxylate, and this group, this carbon, this will oxidize into CHO. So here decarboxylation will take place, carbon dioxide will release, and this carbon will go to the CHO, right? And minus this calcium carbonate. Decarboxylation will take place, right? So this is the basis of rough degradation. Now you can show with the reaction, right? So in this way you can convert 6 carbon carbohydrate to 5 carbon, 5 to 4, 4 to 3, like that, right? So in this way you can convert this. Another method is WOHL degradation. Degradation. So what is the basic chemistry involved here in this? Suppose that we have COH, OH, H, this type of compound. First, we have to convert this into CN, right? In this compound, right? So first CHO is converted into Cn. How to convert this CHO into Cn? How to convert this? There are methods. Suppose that we have first we react with this NH2OH and then dehydrate, so you will get this Cn. And after that, if you use certain strong base, some strong base. So under some strong base, this Cn will be eliminated as a HCN from here. This carbon is go out, and this is converted into CH. So this is the basic concept of this. First convert CHO into Cn. After that, use some strong base so that HCN will eliminate and you get this compound. So let's see how to convert this into this and then this. This is the outline of this OHAL degradation, right? Now see, suppose that we have D-glucose, COH. This is D-glucose. First, you react with this NH2OH. So this group will react and you get C double bond N OH. Right. After that, react with this mild dehydrating agent AC2O, acetic anhydride. So dehydration will take place, and here you will get Cn. This OH and H will eliminate. Right? And after that, if we use a strong base like OMe minus, so this will attract this H, right? So minus HCN, Cn minus from here, H from here, and this will convert into CHO. Right? So this is D-arabinose. D-arabinose. So this is D-glucose. So D-glucose to D-arabinose, you can easily interconvert. So this is the conversion of interconversion of one type of carbohydrate into other type of carbohydrate. In one case, you can decrease the number of carbon atoms. That is known as rough degradation or whole degradation, and one increase the number of carbon atom, that is called Killiani-Fischer synthesis, right? Okay, now similar some more reactions I will discuss here slowly, and some reactions, chemical reactions, which are explained by this open chain structure. This is the glucose open chain structure, and in your syllabus, glucose and fructose structures, cyclic structures are also kept. So now all these reactions are explained by open chain structure as well as cyclic structure. But we have certain chemical reactions which cannot be explained by this open chain structure of glucose. So then we have to shift over the cyclic structure. But slowly, I will let you know that how to reach to the cyclic structure of glucose. Now, all these reactions, whatsoever reactions I have discussed here, all these reactions are shown by cyclic as well as acyclic structure of glucose. But I have certain structures, certain reactions which cannot be explained by this open chain structure, and certain properties of carbohydrates which cannot be explained by these open chain structure. Then we need cyclic structure, right? So see some more reactions of this carbohydrates, and one is very popular reaction, that is osazone formation. Osazone formation. This is very popular and very important reaction. Definitely you will get, you may get the questions based on this. Osazone formation. Osazone formation. This is very, very important reaction. And and this is a very general reaction. All of you have gone through this reaction in carbonyl compounds, that whether you have aldehyde or ketone, aldehyde or ketone, whatsoever compound, if you react with this NH2 NHPH phenyl hydrazine, then you will get, right, what you will get. Osazone. Formaldehyde, hydrazone. First we write hydrazone, hydrazone, right? Acetaldehyde hydrazone, ketone, acetone hydrazone, like that. And when this carbohydrate molecule reacts with this, then they form osazone. So you can see that glucose, if you take glucose or mannose or fructose, glucose, mannose, or fructose, whatsoever you can take, any one of this monosaccharide you can take, and take this pH, NH, NH2, then you will get osazole. Or you can say glucosazole, right? Means what I am trying to say means fructose is also give the glucosazone. The answer is yes. What mannose is also give the glucosazone. Answer is yes. This is very tricky reaction. Glucose, mannose, fructose all will form same osazone. Similar type of crystal. Similar type of crystal, same formula, same chemical formula, everything is same. But the starting materials are different. So sometimes question is asked that osazone formation, this is the best reaction to distinguish between glucose, mannose, and fructose. Means this is a very good reaction through which we can differentiate glucose from mannose, from fructose, right? How it is possible that if all three are forming same osazone, that have same melting point, same solubility, that osazone, white needle-like crystals we are getting in this reaction. So how this osazone formation is a best reaction to distinguish between glucose, mannose, and fructose? The answer is lie in the kinetics. The rate of reaction is different for different for glucose, fructose, and mannose. See, fructose forms osazone, glucosazone. Fructose forms glucosazone within 2 minutes. Glucose forms glucosazone in 4 to 5 minutes. In 4 to 5 minutes. And mannose forms glucosazone in 6 to 7 minutes. So on the basis of the time required, time used in the formation of this osazone, glucosazone, we can distinguish glucose, fructose, and mannose from each other, right? Now see how this glucosazone is formed. So see, in this reaction, see, first two carbons are used and the rest part is not used. So I am trying here the structure of glucose, D-glucose. See, this is the D-glucose, and you know, fructose, glucose, and mannose, they differ first two carbon only, and these two carbons are involved in the osazone formation. Therefore, all three form the same osazone, right? So, first molecule of phenyl hydrazine This will react with this water eliminated. So you get C double bond N NH PH H right, like this. Clear? Now the second molecule of phenylhydrazine is used, and this will oxidize this group, secondary alcoholic group, into ketone, right? So C double bond N NHPH, and this will oxidize to ketone, and the rest part is same. So in which this compound is reduced, this compound is reduced in pH NH2, and ammonia is liberated, right? So two molecules of phenylhydrazine are used. And see, one more question is sometime asked, okay, how many molecules of phenylhydrazine are used to prepare this osazole, glucosazole? So because if you remember directly the formula, so from formula you cannot identify, because now the third molecule of phenylhydrazine will attack on this ketonic group, and this will C double bond N NHPH, N NHPH. So this is the formula of glucosazone. Glucosazone, right? So whether you are starting from mannose, whether you are starting from fructose, whether you are starting from glucose, right? You always get this glucosazole. So from this structure, you can infer that okay, only two molecules of phenylhydrazine are used, but see here, one mole of this phenylhydrazine is used to oxidize this secondary alcoholic group into ketonic, right? So similarly in fructose, also one molecule is used for the same cause and for the mannose. So total 3 moles of phenylhydrazine required to form glucosazole. Glucosazole, right? Total 3 moles. Okay. So 3 moles of phenylhydrazines are required to make the osazole. So this is the all about osazole formation. Now come to the next reaction, that is oxidation. Oxidation, right? See, if you take glucose, D-glucose, D-glucose. So if you have D-glucose and if you oxidize by using Br2 water, this is a mild oxidizing agent. So this will oxidize into COOH and the rest part is same, and this compound is known as gluconic acid. Gluconic acid. If you use some strong oxidizing agent like concentrated HNO3, so you will get COOH, and this last carbon, this is also oxidized, and the rest of the carbon OH, they are not oxidized, and all of you are knowing that primary alcoholic group is more prone to oxidation compared to the secondary and tertiary. So this compound is known as saccharic acid. Saccharic acid, right? So this is the oxidation of D-glucose. Okay. Now see reduction. Reduction. So if you take this D-glucose and rest part is same, and if you reduce this compound with sodium amalgam and HCl, or with sodium borohydride, so this group will reduce into CH2OH, so we will get CH2OH, right? So this is called sorbitol, sorbitol, right? Sorbitol is a instant energy source. So most of the health tonics and players, they are using this compound as an instant energy source, right? Now see ester and ether formation. So you know here alcoholic group is there in carbohydrate, so they can easily form the ester, and we can form ether as well. Suppose that if we have D-glucose, see every time I am taking a reference D-glucose because you know this is in your syllabus. So this is D-glucose, right? So if you take excess of acetic anhydride AC2O and pyridine as a solvent, so what will happen? See, All of you are knowing this is a protection of OH group by acetylation reaction. So here you will get ester. So this hydrogen, this hydrogen, this hydrogen, this hydrogen, and this hydrogen. All they replaced with this group CS3 CO group. This is called AC group. And AC2O is COCS3. So this is the formula of this. So what we get, COH O O AC 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 AC, and this is called glucose pentaacetate. Glucose pentaacetate, right? Glucose pentaacetate. So this is ester. This is basically ester, ester formation. Now see, if you take this molecule and react this molecule with excess of CS3I, excess of CS3I with moist silver oxide Ag2O. So what we get, OCS3, CS3, 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 CS3. So if you take excess of CS3I and Ag2O, then you will get ether. And if you take excess of AC2O and pyridine, in pyridine, then you will get pentaacetate, right? So this is the reaction of this glucose with in the formation of ester pentaacetate as well as what this ether, right? So in this way you can prepare glucose pentaacetate, and this reaction you can use for the quantitative estimation of number of OH groups present in any molecule, not only in carbohydrate but for any other molecule, right? So these reactions, what I have shown here, all these reactions are used to, show by, all these reactions are shown by acyclic structure, means open chain structure, as well as what cyclic structure. Now, see, slowly I am shifting you some other reaction on the some other reaction. See, next reaction is sodium reaction with sodium bisulfite. Reaction with sodium bisulfite, NaHSO3. So all of you are knowing that if you take this sodium bisulfite and any aldehyde or ketone. If you take sodium bisulfite, remember this reaction, already all of you have gone through this reaction, so you are getting salt, right? But if you take glucose pentaacetate, now see, this is glucose pentaacetate, glucose pentaacetate, right? If you take glucose pentaacetate and try to react with this sodium bisulfite, no reaction. See here, all of you are knowing that in this reaction the involvement of this CO group is there. So in the open chain structure, the CO group is here in the glucose pentaacetate, but this will not react with sodium bisulfite. So glucose pentaacetate do not react with sodium bisulfite. What it means? It means it creates doubt whether this CHO group is free in glucose or not. We are anticipating that if this CHO group is free, then this glucose pentaacetate must show this reaction. Okay, so now see, slowly you will get so many reactions which are not shown by this open chain structure, and which suggest that okay, this glucose has cyclic structure. So slowly I am moving towards the cyclic structure of glucose. Right, now see another reaction, reaction with 2,4-DNP, reaction with 2,4-DNP. All of you are knowing this 2,4-dinitrophenyl hydrazine test. If you take glucose and 2,4-DNP test, if you want to perform 2,4-DNP test, so you will get negative, right? So 2,4-DNP test, this is negative. But aldehydes and ketones both show this test positive, right? Similarly, Swift test, Swift test, all of you are knowing that aldehydes positive, aldehydes positive, and ketones negative, right? Glucose, glucose, oh, excuse me, shift test negative, right? Similarly, reaction with NH2OH. You know, aldehyde and ketone, aldehyde and ketone both reacts with NH2OH and they forms oxide. Oxide. But if you take glucose pentaacetate, glucose pentaacetate, and if you want to react with this NH2OH, No reaction. So all these reactions indicates that in glucose pentacetate there is no free CHO group. There is no free CHO group, right? Because if you take glucose, simply glucose, then this will react with NH2OH, no problem. This will react with this NaHSO3, right? But pentacetate, this will not react. So all these, observations suggest that there is some problem with this structure. There is some problem with this structure, right? Now, so all the above reactions, note, we can put a note here. All the above reactions, they, reactions. And one more observation we can point out here, that if we take glucose and if it is treated with methyl alcohol in HCl gas, so this will form acetal with only 1 mole of methyl alcohol. Acetal. Remember carbonyl compound reactions, reaction with methyl alcohol with HCl gas, you will get acetal, but 2 moles of methyl alcohol are required. First you will get hemiacetal and then you will get acetal. So with only 1 mole of methyl alcohol. This suggests that it means glucose molecule already have hemiacetal ring. Hemiacetal ring, right? So all these observations supports. Now we can put a note that all above reactions suggest that glucose exists in cyclic structure, right? One more physical property also we are observing that also supports the cyclic structure of glucose, right? So this is also very important observation that helps or that supports the cyclic nature or cyclic structure of what glucose, right? Clear to everybody?